Alright students, I thought it only appropriate to kind of throw a video out here since this assignment is more complicated than most and not really exactly in a SOLIDWORKS way. Some of these topics are just things you might not learn until a 4,000, 5,000 level class. Not necessarily the difficulty, but just the procedural things, like how to set up CFD and everything else. So I'm just going to do the homework and you can follow the video. I'm just concerned that you guys get through it. So let's see here, the download F1 wing model, got it. The subtle changes again were the fact that I've cut out these ribs to allow those wings to pass through unhindered. We need to run a CFD and an FEA study on it, so first I'm going to turn on my add-ins. I think I've already got flow simulation loaded in. I'm doing another exercise here. I'll turn on the SOLIDWORKS simulation. And it'll load up. Alright, got it. This is the other study I just finished doing. It's a CFD nozzle study for a supersonic Mach 2.5 nozzle for the compressible flow class. They calculated the shape of this, and then instructor Cody wanted to see what it would look like. So you can run that in CFD and done. Cool. But we don't need that now. That's irrelevant. Let's do a flow simulation. So first thing you do, we've already got it kind of set up here. Nothing really special to do. We'll hit Wizard. Project name, F1 wing. Sure, why not? You could leave it untitled, doesn't matter. SI units, yep, next. We want external flow. We don't care about heat conduction, radiation, time dependency, gravity, or rotation. We don't care about that. We don't have any internal spaces to tell it to avoid. Reference axis, as far as I know, only matters if you're going to start spinning things around, which hopefully our wing doesn't start spinning. That would be unpleasant. Next, gases, air, sure. Changes to turbulent only. That hurts the accuracy of the solution some, but anything hitting this wing is probably going to be rather turbulent, and it makes the solution a lot faster. And this is an educational exercise, so we already know it's going to be a little bit wrong. Wall conditions, don't care. Velocity in the z direction. You see this triad down here? The z vector is pointing the way we want to go. So I think peak speed on these F1 cars is around 220 miles per hour when you put it in that units. So this translates to 102 meters per second, which is what the homework says to set it up as. So interestingly enough, I just made a mistake. You have to have negative 102, because if it's positive 102, it's going to be flowing in the z direction, so your wing will be going backwards, which they don't work as well going that way. Standard temperature and pressure is fine there, so we'll just leave the grid normal for the moment, and we get the wall around it. So to emulate the ground surrounding this thing, we need to edit the computational domain, and I'll just kind of drag this arrow up a little bit. Mistakes have been made. And again, I'm going kind of fast because this is a video. You can pause it, you can rewind it. I don't want to waste anybody's time. I want to make this kind of as concise and as efficient as possible, which is why I'm blabbering right now. Okay, so that snapped to the bottom of the wing. Let's, actually I think I gave it a specific distance, didn't I? Yeah, 0.8. So y minus 0.8 actually elevates the wing above the ground a little bit. Let's change that to a symmetry plane. This again causes the ground to become kind of like a reflection, meaning no flow can pass through it, which for other fluid reasons you'll learn throughout your education means that it is a ground plane. It's like emulating the ground right there beneath the wing. Alright, got that done. Set up symmetry plane. Step C, mesh settings that worked good enough for me are listed on the next page. So let's just skip straight to those so we don't have to sit here and iterate some mesh stuff. So obviously just the simple slider, I gave you some more detail in that, so uncheck automatic settings, and now you get more detailed stuff. So following the things that are on the second page of the PDF is 42, 25, 54, solid fluid interface, small solid refinement level 4, or yeah, it's actually going to be 3, this one gets ticked up to 2, okay, refining cells, we had none of that, and narrow channel refinement, it's enabled at level 5, okay, so that's the mesh setting, and I suppose that's it. We just run it. Oh, no, I remember a mistake I made now. I left out one thing, which is always the case. You always start the study and you realize you just screwed something up. So stop this. Yes, I want to stop the calculations. Okay, it's stopped. Close that out. I forgot to tell the model not to worry about the presence of the internal structure. The fact that it has this solid wing and the internal structure inside of it is probably going to throw it for a loop. So you can go to flow simulation, component control, and find which one of these is the internal structure. There we go, there's one. Uncheck that. There's the other piece of internal structure. Uncheck that. I don't know. I've actually not tried to run it with that still turned on, but everything else I've done in SolidWorks tells me that when you have two solid bodies interfering with each other and you try to run analysis on it, things just aren't going to work great. The fact that both of the surfaces exist on the outer mold line of this model would probably throw CFD for a loop. Okay, let's run it now and see if it works. Meshing, solving, new calculation. Yep, let's go. I can bring the calculation window over once it's running. Alright, so preparing model. It's going through the meshing procedures. Boring. This is part of the video you're going to skip over. Alright, we're back. Solver's finished. I tried to get away without waiting for all this, but it took a total of 2 minutes. So, not long. So anyway, let's turn on a cut plot. These are the plots you have to make to turn in. Let's make it on the right plane. So expand the tree, click right plane, yay. Contours, pressure, Now this is the number of color gradients. 10 is the default, which makes it look really terrible. So 36 would be good. Set it to plot min and plot max with those two buttons there. Get a preview of what's going on, and alright, that looks fine. Actually, I hate that kind of puke yellow color. But whatever. Let's say okay. Wonder why. Anyway. Next thing we have to turn on is a surface plot. Let's insert that. Might as well just select all faces. Pressure, yep. Okay. It'll integrate this pressure on all the surfaces, and you see that, high red pressure on top of the wing, low blue pressure on the bottom. Well, that's how wings work, so that's probably right. Now, I generally just hide this cut plot. I mean, for turning in images, what I say in the homework to turn in a JPG screenshot of the side cut profile. So I would set this down here, and I would start up snipping tool, and just snip a picture of that. And turning that in for the homework would be fine for the cut plot. Then you also want to do one for actually showing pressure and streamlines. I didn't have the streamlines turned on. You just mash this button right there. Now you have streamlines. Properly tuned limits, surface plot showing pressure from 3D viewpoint with flow trajectories. Okay, so to make that image, we need to hide the cut plot. We've already got surfacing turned on. This thing's out of the way. Notice you have to actually click on the little bar to move that around. We can turn on flow trajectories, inserting one. Let's have them emanate from, well, those surfaces for sure. These big wing surfaces as well. Outside panels, and yeah, it should be fine. Let's do like 50 of them. Pipes are okay, but I think bands are more interesting. Marching bands are really the best, but these will do. There we go. So bands, I think we have them pressure colored by default. Yeah, so the color evolves as pressure changes on these things. So there we are. You see actually the vortices generated by the ends of the wingtips and everything there. It looks pretty slick. So then at that point you just take a 3D isometric shot, just do snipping tool again, like this perspective would be fine. And we need to lastly do an Excel file showing the force integration on the wing. We need to actually figure out how much downforce this sucker's making. So to do that, you do surface parameters, insert. We need to go down and look for force, which in my situation is already here, but if it's not already loaded on yours, it'll be underneath loads. Force is right there. Look at all this stuff you can calculate and integrate for parts. It's pretty cool. So you check force, it'll be newtons. Nice. Select. Let's choose the surfaces we want to integrate force over, so we can do this one, this one, this one, this one. And also getting the bottom side is important as well, because the low pressure there will actually help suck you to the ground a little bit extra. You could go ahead and click these end plates again, but like I said in class, the only forces that really matter are the ones pointing up and down. So since most of that area is left and right, and it should offset itself, hopefully it won't matter too much. It would matter to drag, but show results, negative 7,916, which is a little bit different than what we got in class, I think. Value force, actually that's 8,196. Okay. In the y direction, which is the up and down, it's at 7916. Z is the drag direction, so that'd be 2125. So, pretty cool results. We actually figured out the total downforce on stuff. You could go around, just continue adding these surfaces and click show again. It recalculates things, and the result changed, by extraordinarily small amounts. So what do you know, the wing is the most effective thing at making downforce, lo and behold. But anyway, the thing we're more concerned with now is how to transfer these loads to finite element analysis. So before we leave flow simulation, let's go to FlowSim, Tools, Export Results to Sim. You'll do some things and pretty much finish up there. So let's go to simulation now and set all this stuff up after turning off Computational Domain, not edit, hide. So that way it gets out of our way. Let's go to Study Advisor, New. I want to make a static study. Be very accepting of that. Alright, so the first thing I need to do is set materials, which I think we can select all of these, right-click, apply, edit material. I think, did I say material in the homework? Probably not. Aluminum. That's what I discussed in class. It's like 2024. Again, the intricacies of materials and how to apply them properly in FEA sims comes whenever you take the courses, specifically for finite element analysis or stress. You'll understand a lot more at that point. So the next thing we need to do is actually start considering how to hook up the internal structure to the surface of the wing. Right now, remember this wing is a solid body. I made the modification in the part you downloaded. So obviously you're not going to cut this wing out of a solid chunk of aluminum and put it on your F1 car. The way you figure that out is we can find the solid body that is the big wing, right click on it and say define shell by selected faces. Well, let's select the faces we want to have a shell made out of. In this case it's a little bit different than the shell command we learned in solid modeling. This is actually just making it a surface. Make it 0.05 thick. And that should work. So this actually converted, notice the icon's different. It's no longer a solid body when it's being considered by the finite element solver. It's going to be a thin shell. So we're actually making it like a, like a shampoo bottle, a real thin piece of plastic, or in this case, aluminum. If you want to enter in properties for carbon composite, you certainly could do that as well. So same thing up here, shell by selected faces, select top, top, bottom, bottom. I'll just set that to 0.05 to be consistent. Accept. And then I've also found that the end plates should be shelled out as well to get things to work nicely. So let's right click that, shell the inside of him. I don't think I'll always do both at once, but let's see if this will break. Actually, I think I remember these need to be thicker. Oh, I think it totally worked. Yeah, totally did. Okay, so everything else can stay as solid. We can go ahead and establish next which parts are fixed, which, I mean, we want to do fixed geometry, and in this case, you'd normally get the bottom of your wing here fixed to the car, which that's exactly what it is in our scenario. So fix those bottom surfaces. They won't rotate, they won't move. Whoops. Since we turn these into a shell, it's important to select just the edge. These shells, these end plates no longer have thickness. So we'll select those edges. We'll say OK, and then now it knows to keep that shell, that little, surfaced edge fixed. So that'll work better with the sim. So that's fixed in place. We have material selected. We have things shelled out. We need to apply forces to it. So before we load in, well, it's so easy to do. Let's go ahead and do that. Right click on the main Study 1 default. Go to Properties, Flow Thermal Effects. Check that box and look for the, hopefully this is the right one, the 1.FLD. Oh, that's the nozzle. This one? Oh no. Great. Alright, yeah, that's it. Okay, so hopefully in your case, since you've only run one CFD study, there's only one to worry about. So that's what we need. That looks okay. So that will actually import, if you look underneath loads and expand it, we have the fluid pressure over the whole body. We have fluid shear stress in X, Y, and Z. So that's really slick to be able to do, to actually import actual CFD pressure contours. So fixtures fixed on the bottom, pressures on the sides. Let's go ahead and mess with the mesh. We can say create one. If we just left it here, it'd probably fail. Let's see if that's the case. We'll say OK, and it's going to take away a few seconds of our life. Probably make a liar out of me and work. Oh, nope, there we go. Oh, that's Dropbox. That's Dropbox's fault. Let's try again. So Dropbox kind of hurt me there a little bit, so let's right click here and say create mesh. Actually, maybe it works. Let's see if it works. Let's right click show mesh. Oh, it kind of did. It didn't fail entirely. Oh, but I have failed entirely. I forgot to click on the surfaces for these little vents. So now they're not being meshed at all. So let's go check out the... Is that one of the shells we need? Yep. We have to expand it. Right-click shell 4 and say Edit. At that point, we have to add in these little vents, or else they're not going to exist in the finite element analysis simulation. I know that'd make everyone really sad. Right-click here, shell, edit definition. Again, just adding those in. Fix the mistake, fix the oversight. Okay, that mesh, though it might work, looks terrible. So let's up the resolution a little bit. Right-click, create mesh. I'm going to turn off Dropbox so it won't hurt us anymore. So let's slide that up to a bit better resolution. Let it calculate. Hopefully not failing. Alright, much better. Look at all those tiny triangles. Much better shape representation. You never want to see like the leading edge of your wing be represented by one big triangle. It's generally a bad thing. So, if we ran it right now, we would most likely see a photo that looks like, if I can pull up the reference picture that I made, there's the correct one. A photo that will look like this, where the ribs stick through the surface. When you actually bond these ribs to the surface of the skin, interestingly enough, SOLIDWORKS knows to bond to these edges where you get a 90-degree butt joint. So this wing skin is automatically connected to the ends by this global contact that's automatically put into finite element analysis simulations. Also, since this solid part has the inside cut out for the surface, those are already under global contact. So everything in here is already taken care of by that global contact constraint, except for the bonding of the internal structure to the outside skin. So let's do that. Right-click connections, contact set. Instead of no penetration here, we want to set it to bonded. No penetration means the parts are free floating from each other, so you can make sure that SOLIDWORKS doesn't automatically connect them. Allow penetration means that they're going to be meshed together when they pass through each other. And then virtual wall shrink fit are special circumstances. So manually select, yep. First side, these 4 outer surfaces of the skins, and second side, we're going to have to right-click, select other to be able to select the face, the little edge of those ribs. Thankfully, the entire face, top and bottom, is shared, so we can get those all in one go. Oh, no. Oh, no. What did I click? That's not good. One last thing here. Select other, face. Alright. Wrong button. I'll get it this time. If only this was the most difficult part of engineering. Accept, and we're good. Okay, so that's contact for the bottom wing. Might as well do it for the top as well. I was considering maybe leaving that undone to show you the difference, but let's just take care of this and show you how to do the whole homework right. Those 4, I changed this to bonded connection. This works well because those surfaces exist in the same exact plane. They are the same surface, just one's cut out from the other. So that works fine. Okay, spin that thing around. Alright, so those will be bonded together. End plates are set up to go. Let's go ahead and run it. Hopefully this won't break. Okay. That's finished. It's done. Okay. So look, we have a result. We have deformation in the end plates. We have pressure distribution over the wing surface. Look, we actually see even some stress concentration due to the presence of the internal structure. Yay. I don't know. That's pretty much it. You're going to learn a lot more about stress flow, stress concentration, the material's influence of that, how thick things need to be made, how beams work, and how to calculate finite element analysis, simple situations in the years to come. But for now, you actually just did one of the most complicated things that any student's ever done for a class at OSU, as far as I know. So, cool. done.